The unit of similarity is very important for this course. It will be one of the major points of the regions, and it is related to many other units. For example, the units of dilation. And that is because dilation is a kind of a transformation that produces similar figures. So when we are talking about coefficient of dilation, it is the same as the coefficient of proportionality in our similar triangles questions. It is the same as coefficient of similarity. And it is the same as a scale factor that you might be familiar with from middle school. This means that any time when a figure went through a transformation by dilation, the same laws that work for similar figures, and in our case specifically similar triangles, would apply to the image and the original. This means if you have triangles, then you could use one of these rules to prove them similar. If you have two pairs of congruent angles or three pairs of corresponding but proportional, not congruent, sides, or if you have a situation when one pair of corresponding congruent angles are included between the two pairs of corresponding sides who are in proportion. So these are the major rules that establish that a pair of your triangles are actually similar triangles. It is important, though, to clearly understand that triangles or not, when figures are said to be similar, the following rules of similarity apply by definition. Their corresponding sides are always in proportion. That means they could be compared by division in a ratio. Ratio of sides will be the same as the ratio of perimeters, no matter what kind of figures are similar. It is also true that if you take the ratio of sides, or ratio of perimeters for that matter, and square it, it would be a ratio of areas. You can even find the ratio of volumes for three-dimensional figures if you know the ratio of their linear corresponding sides. You simply will take that ratio and raise it to the third power. Now, these are relationships of lengths, corresponding lengths, perimeters, areas, and volumes of similar figures. Please remember that corresponding angles in similar figures are congruent. Therefore, corresponding angle ratio is always 1 to 1. Now let's focus further on similar triangles, because we will have lots of questions related to that kind of application. When triangles are similar, their corresponding lengths are in proportion, and what makes this material interesting and difficult at the same time is the fact that those proportions could be written in many more than one form. To summarize all those forms, or at least majority of them, please recall that we were talking about writing a side of a small triangle to a corresponding side of a big triangle, a side of a small triangle to that part of a big triangle that serves the expansion of that small side, and then one side of a small triangle to a different side in the same triangle is in the same ratio as corresponding sides in the big triangle. So your examples might include situations when triangles are separated, like in this case. If I were to establish the similarity with the similarity statement above, then following corresponding elements, I would be able to rewrite these proportions in the following order. Please examine them to review this material. Feel free to pause the video whenever you need to examine this information further. You could have a situation that is more interesting. Two separated triangles, but they are right triangles. In that case, the ratios are written the same way as in the previous example. You could check it for yourself. But the relationships to review are much more complex because they bring us to the relationships inside right triangles as well. You see, you could recall what sine of angle C, for example, would be. That is a ratio of opposite side to its hypotenuse. At the same time, you can and should recall that sine of angle C equals to the cosine of its complement, which is angle B. At the same time, since corresponding angles in similar triangles are congruent, angle C then is congruent to angle F. So sine of angle F then would be congruent to everything we've discussed before. At the same time, sine of angle F is also a ratio of opposite side ED to hypotenuse EF and could be written as this ratio. And of course, sine of angle F equals to the cosine of its complement, angle E. So this is quite a bit of interesting conclusions we should be able to make about this pair of triangles just based on the fact that they are actually a pair of right similar triangles. Of course, you should remember that in any right triangle, similar or not, it is true that the hypotenuse squared equals to the sum of legs squared. And I didn't write similar statement for the other triangle, but it will express the same idea. Well, your triangles do not have to be separated. It could be one single triangle with split side, and a segment like PH parallel to a third side could be used for split. Or the sides could be split in a non-special way when nobody says that HP or PH segment is actually parallel to the third side. So in that case, you would have to be very careful rewriting a statement that indicates which angles are corresponding, which I was very careful with. You could see angle SP are congruent, they are corresponding, and in the triangle on the left, I see angle S and P will be congruent because they are corresponding, formed by parallel side and transversal TS. The kind of relationships that could be examined in this triangle also could be described by these basic ratios, and I ask you to pause the video to examine and verify for yourself the ratios that I wrote for these pairs of triangles. It is important to know, though, that it's much easier to write these ratios from the diagram of the original of the triangle on the left, but it's better to use the statement itself to write those ratios for the second case. You probably wonder if this case could become any more interesting. So in a way similar to the previous situation, when the two triangles seem to be one on top of each other, I could have a situation with the right triangles as well. So on the left, it's a pair of right triangles, one on top of the other, formed by splitting the side with a line or a segment actually parallel to the third side. Whereas in the situation on the left, split happens but not with a parallel side, and you see that these two angles right here are not corresponding yet congruent, perhaps by the given information. Unlike these two, for example, we need to know without being given that they are equal. Same goes for these two angles. So the ratio could be rewritten the same way for these triangles as well. You could write those ratios on your own without looking it up here and then comparing it back with me. But what I want to review is the fact that is formed in the right triangles in regards to sine and cosine of complementary angles. So if I'd be looking at sine of angle R, sine is a ratio of a side opposite to the given angle and the hypotenuse. So the ratio would look like TS over SR. At the same time, sine of R must be congruent to cosine of S corresponding angle. At the same time, as similar triangles, angle R would be congruent to angle H. Even on this diagram, although it's not that obvious, because the reasons for congruence for H and R would be different. They are by the given, whereas here, by the relationship of corresponding angles. Well, since cosine of an angle is a ratio of a side adjacent over the hypotenuse, then we will write the statement that ST over SR is also cosine of S. The same could be continued for the sine of angle THP. THP right here. And angle TPH. TPH. This P should be right here, of course. And yes, it is true that Pythagorean theorem also works because it's a pair of right triangles. There is a special situation to a side split triangle. If you have a side split by a segment parallel to a third side, which goes through the midpoints, this is the segment I'm talking about, and goes through the midpoints of the side, then we call this segment a mid-segment of a triangle, and its length will always be half of the length of the third side, who he is parallel to. So that's a very handy rule, which I wrote down in words right here. To continue, if I have a situation when the triangle is inside the other triangle, we must mention a case of a right triangle with an altitude. Because every one of these ratios would work there as well. So I would be able to write all of these guys if I separated this left triangle and the right triangle and compared them on a separate occasion with the original big triangle. But I'm not going to be doing that. we did it in class when we observed that all of those relationships could be described in a more comprehensive way. So I'm going to state the similarity sentence for the three triangles, left, right, and the original. And I'm going to bring a situation when a leg of the original triangle is actually a mean proportional between its projection and the hypotenuse of the original triangle. That is a very important rule as well. And this is how that substitution will look like for this particular case when the leg is GK. Of course, a similar statement could be made about the leg GL if it had been given to us. Now there is a visual mnemonic to remember here. To recall this rule, the leg is a mean proportional over its projection and the whole hypotenuse. Same picture, but a different piece of information. What if you didn't have anything, not even a question, about the leg of that triangle, but you would have an altitude instead? Then the rule that you would apply would be altitude is a mean proportional between the parts of the hypotenuse formed by that altitude. To remember this rule, you might want to use this symbol. So altitude is your mean proportional in the two parts of cut hypotenuse. The same rule after the substitution will look like this proportion. Of course, it is true to say that if you're working with a sine of an angle, L in this case, then it will equal to the ratio of side opposite to the hypotenuse and could be written this way. At the same time, if you look at sine of angle L inside a smaller triangle, then it also will be side opposite over the hypotenuse. And of course, it will equal to the cosine of its complement, angle K, in the right triangle KGL, for which we also can write a ratio adjacent side over hypotenuse, and we will receive these two statements. It certainly is true that cosine of angle OGL, I'm slowing down because you really need to find it on the diagram, OGL is a complement to angle L in a smaller triangle, will also equal to sine of angle L. This is a lot of information, and I think you should pause and go over it once again, this time all by yourself. It certainly is true that in these three right triangles, Pythagorean theorem also will work. In this case, I wrote it slightly differently. I wrote the first statement for the hypotenuse GL squared in a triangle on the right, where legs GO and OL squared are added. But then I switched to the big triangle, where GL actually is a leg. So GL squared in that case will equal to the difference of hypotenuse squared and the other leg. To sum it all up, similarity is a very interesting and rich topic, full of connections with all other topics in geometry we've studied, so please devote significant time to it.